Welcome back to MATLAB Programming for Engineers. In this unit, I want to talk about applying some of the MATLAB programming techniques that we've covered up to this point to the solution of a moderately complex mechanics problem. And the technique that we're going to focus on is called iteration, which essentially means successive approximations. You make an initial guess for the solution. Based on that initial guess, you calculate a better approximation. You then take that approximation as your next guess, which allows you to calculate an even better approximation, and on and on. The specific problem that we're going to tackle is a simple Physics 1 problem on projectile motion. That is, imagine you're trying to shoot down an incoming aircraft with an old-fashioned howitzer-type anti-aircraft gun. So it's not a guided missile, it's simply a free-falling projectile. And the only thing you have control over is the angle at which you fire the projectile. And you've got a target that's coming in at a certain altitude, h, certain velocity, vt, it's at a certain range, r, and you want to calculate at what angle should we fire our projectile to hit the aircraft. Now, if you're interested in mechanics, I encourage you to work through all of these equations, understand exactly what I did here. If you're not interested in mechanics, just go right to the solution, which is this equation. Now that doesn't look so bad. What's the problem? The problem is we've got trigonometric functions of theta, which again is the thing we're trying to solve for, on both sides of the equation. We cannot solve this exactly just using mathematics. Turns out if vt, that is the target velocity, is 0, that's a special case where it is possible to solve exactly. But if vt is non-zero, you have to resort to a numerical solution. So that's what we're going to try to do. And I'm going to show you a few ways of doing it. The first couple do not use iteration, and those are not acceptable for this assignment for two reasons. First, it doesn't use a loop, which is one of the learning objectives of this assignment. And also, I'm going to give you the solution. You can't just plagiarize my solution. So I'm showing you these first couple of methods just to try to give you more insight into what's going on and what it is we're trying to accomplish. And then I'll just kind of point you in the right direction for the solution that you have to do on the assignment. So let's go to MATLAB. And I've just set up the parameters here. The first way that we might solve this equation, and let me just show you the equation one more time as a reminder, okay, would be simply plot the left-hand and the right-hand sides versus theta, and see where they intersect. Where those two lines cross, that's the solution. So let's try that. All right, I've set up the parameters. I've set up an initial grid of theta values going from 0 to 90 degrees, and I'm going to represent theta in degrees here rather than radians. And then the right-hand side, and I've actually gone a little bit farther than the equation that I just showed you. I'm actually solving for theta by taking the arc sine. All right, so this should be my approximation for theta. So I'm going to plot theta, and on the same graph, I'm going to plot this right-hand side, which is my solution for theta, my approximate solution for theta. And where those two things cross means I have the correct value of theta. So let's run that and see what happens. All right. So where those two cross, and theta is on the vertical axis here, so I go across to the vertical axis, and you see the solution is somewhere between, looks like 20 and 30 degrees. Okay, right there, that's the solution. If I want it with more precision, now that I know it's, say, between 20 and 30 degrees, I can just zoom in and do a solution over a more limited range. All right, so now we can see it's somewhere around 26 degrees, 25, 26 degrees. So we can even zoom in a little more. All right, and we've got it around 25.6 degrees. And if you needed really high precision, you could keep solving with more and more over a smaller and smaller interval. Well, that's not really an acceptable way of doing it for this class. In a mechanics class, that would be just fine. You got the solution. But this is a programming class, and we don't want the user of our program to have to keep intervening, right? And just read the solution off of a graph. We want the program to simply tell us the solution. So this technique isn't quite going to get us there. Let's try something else. Another thing we might do, what if we simply take the difference between our approximate solution and the value of theta that we're basically putting into this equation. And based on the graphical approach that I just showed you, when these two things are equal, that means we've got the correct solution. So what do we do? Why don't we do this? Let's look at the difference between the two and try to find out where the minimum of that difference is. All right, so I define another variable called difference, which is the absolute value of the difference between my guess for theta and then my approximate calculation of theta based on that guess. And I want to find where the minimum of that difference occurs. And remember, when you call the min function, you can do it in such a way that it gives you both the minimum value and the index where that minimum occurred. And then you use that index to index into your theta vector to get the value of theta where that minimum occurred. All right, so let's try this. And you see I get a value of theta of 25.45 degrees. Now I'm going in relatively large steps here, almost 1 degree, so this wouldn't be a very precise solution. But now that I know approximately what it is, I can calculate again over a smaller range, let's say between 25 and 26 degrees. Okay, and now I've got a solution of 25.65 degrees, which is quite accurate. Now that's also not going to be an acceptable solution for this assignment. It's not a bad way of doing it, but the one drawback of this solution is you're doing too much calculating. And we'd really like to do the minimum number of calculations. And that's why we use an approach called iteration. The idea of iteration is this. Make an initial guess for theta. And for this problem, 0 is not a bad initial guess. Let's just assume the angle is 0. Put that into this equation. Okay, it's the same equation we had before. Right? Put our guess into this equation, and that'll give us an approximate solution. So let's see what we get. All right, so if I guess 0, what I actually get as a solution is 27.74 degrees. The next step is take that approximate solution and make it my new guess. All right, so now I'm guessing that theta is 27.74 degrees, and then I use that to calculate a better approximation, which is 25.30 degrees. Then I take this as my next guess. Calculate a better approximation, 25.7 degrees. And this just goes on until the difference between my guess and my approximate calculation is very small. That is, to the precision that is specified in the problem, which in this assignment I believe is 0.001 degrees. All right, so that's the actual approach you're going to use, but of course you're not going to just keep copying and pasting the successive approximations. You're going to make a program to do that using a while loop. All right, so imagine doing what I just did automatically under the control of a while loop, and that's essentially what you need to do in this problem. Once you've got that working, then of course you want to turn it into a function. So add a function definition. And of course, these parameters that I defined up here are now going to be inputs to the function. You're not going to hard code these values. They're going to be passed to the function as arguments. Okay, so with hr theta m, I'm sorry, not theta m, vm and vt as input arguments, and with, of course, theta as the output argument. All right, so that's the core of this problem. The rest of it then is running a script that will call this function on some test data that we provide you. We provide you a data file that contains 5 test cases, and in your main program, you'll do a loop to iterate. Again, slightly different use of the word iterate here. but just to loop over the different test cases, solve each one, and then you're going to write the results to a file. All right, so you'll be working on that this week. Let us know, reach out to us if you need any help with that. And I'll see you in class.